it's my pleasure to introduce Laurent Younes from...
oh, Johns Hopkins, sorry, I forgot.
You don't show me your affiliation?
Yeah, Johns Hopkins University.
Exactly, Johns Hopkins. And Laurent is going to talk about diffeomorphic learning. So
yeah, don't tell people at Johns Hopkins that I forgot to put that on the slide. Okay, so thank you for the invitation to this very interesting workshop. I am going to talk a little bit about something unusual for me, at least, compared to the kind of thing I'm doing, although it's mostly in the continuation of the method in shape analysis I've been working on over the past years, which is just using this hammer that we have defined for shape analysis and used repeatedly in mini shape nails, and see if that can work in machine learning. The introduction is, so I heard recently about neural networks, and people told me that they work quite well. I don't know if you know about them. I mean, for those of you who were living in another planet over the last few years, and what they showed is, among many things, is that it was not such a crazy idea to try to estimate on, for machine learning problem, very high dimensional transformations, and still have something that can generalize correctly. So there are some issues, like, well, you don't really know what kind of transformation you're estimating, but the method works. And since I've been working on diffeomorphisms applied to simply in 2 or 3 dimensions, just transforming shapes, and for example, the algorithm and the structure of some of the neural network that I used in practice really relates to what the kind of approach we are using in shape analysis. I wanted to try and see what this approach, which essentially requires estimating diffeomorphism, does for machine learning problem, given that that would be switching for low-dimensional 2 or 3 problems to problems that may be much higher dimensional. And so there's a very large body of work on the use of diffeomorphisms in shape analysis. And for example, just a random example, my book on the second edition of my book on shapes and diffeomorphism has just happened, appeared. So that's one possible entry on the literature. On machine learning, there application of diffeomorphisms in machine learning is that I've just seen a few. An important one, Warner and Sholkoff in 2009, in which they were applying diffeomorphic transformation to dimension reduction, and some applications also in the definition of positive kernels, that by Alain Trouvé and you. So I'm going to present the method. And so what we want to estimate is some predictors that take the form, so that consists in applying first a diffeomorphic transformation of the data, and then applying a classifier. Where here, so F is a classifier, so something that takes values in is defined in RD and takes values in a finite number of classes, and so phi is a diffeomorphism. And of course, there will be some parameters, additional parameters in the classifier, so that there will be a theta that will come into the picture. And just a reminder of the definition of a diffeomorphism. So silly notation and a summary of the training procedure if to learn this kind of function. So you have a training set that consists in vectors in RD and classes, and I'm going to assume that no vector is repeated. It's mostly for convenience so that I don't have to have a different notation for the vectors with repetition and the vectors without repetition. And so if I have a diffeomorphism of the ambient space, I can transform this training set by just transforming the vectors, the x's. And what the algorithm will minimize is an objective function that will essentially learn the linear, it's going to be a logistic regression classifier as it's written here. So the classifier, so the theta, applied to transform data where the transformation is penalized by its distance to the identity. And this distance to the identity is going to be a distance, a Riemannian distance in a group of diffeomorphism on RD, and I will spend some time describing that. So just to fix the idea for the loss function, you can use a logistic loss function. So let F implement logistic regression, for example. So now let me summarize how you can build distances between diffeomorphisms, and so let me introduce some notation. So we want to have smooth diffeomorphisms, so we are going to consider P differentiable transformation. So we start with vector fields on RD, so these are not diffeomorphisms, and that go to 0 at infinity, so they form a Banach space. But to be able to define Riemannian distance, we also introduce a Hilbert space that is continuously embedded in that space, and that has a norm and an inner product. So because we have an embedding, I can already introduce a notation. This condition here implies that V is a reproducing kernel Hilbert space. If you're used to reproducing kernels, this is a little unusual because it's a reproducing kernel Hilbert space of vector fields. So the kernel, instead of being a scalar valued function, is a matrix valued function, but the rest is essentially the same as what you have for reproducing kernel Hilbert spaces. And these are two properties that characterize the kernel, and essentially the kernel realizes the representation for this linear form. So returning to the formulation of the distance, you use the fact that diffeomorphism can be generated as flows of ODEs on RD, and so let me go back to, so if you're given a vector field which is smooth enough, then its associated ODE has a unique solution, so it's a time-dependent vector field. Its associated ODE has a solution over T in 0, 1, and for any initial condition. And the flow is essentially the solution that starts at X, evaluated at time T, or the solution of this equation. And in terms of smoothness, or at least regularity of the vector field, this is the condition that we'll impose. This is a condition which is a Sobolev type condition at each time for the vector field V of T, and the fact that the norm square is integrable. So all the set that a vector field that are generated by such a V, so V in L2 of 0, 1, and V, and the flows associated to such V's, if you put them together, they form a group. We won't use that, but this is a group that depends on the choice of Hilbert space that was made at the beginning. And the distance itself is the length, the minimum of this quantity when, at least when you start from the identity, the distance between phi and the identity is the minimum of this quantity when you constrain the endpoint of the diffeomorphism to be equal to the diffeomorphism you're targeting. If you have two different diffeomorphisms for which you compute the distance, you just make a right composition by the inverse to go back to the identity. So to summarize this is providing this geodesic distance, this Riemannian distance on the group of diffeomorphism. And so that defines that specifies the problem that I instantiated before. And in fact, there is this equivalent formulation. Instead of the distance to the identity, you can use the fact that the distance between phi and the identity, you can use the fact that this distance is characterized by a Riemannian metric, and so you can put the metric directly there, and you end up with this problem, which is equivalent to the original one, to build a classifier. So you minimize, you're looking for a transformation phi that minimizes expression, or equivalently for vector fields v that minimizes this expression, and what you would be interested in is the final value of the flow of this vector field. And it's not very hard to prove that there are solutions to this problem. So, okay, one more step before getting an algorithm is that you have a reduction that can be applied to this problem. So so far we still have an infinite dimensional variable here with respect to which we have to minimize. If you look at the trajectories of of each data set, each point in the training set, which is defined by this equation, so it's just a solution of the ODE associated with V, you can prove that this trajectory is sufficient to characterize the solution, and that the optimal V has to take this form, which is to the kernel with one of the coordinates given by Z, and then this unknown coefficient A1 to AN that have to be determined. And if you use this expression of V, use the properties, the reproducing properties of the kernel, then you end up with this final problem to solve, which is which gives this quantity to minimize. So there is a double sum over between where the z's and the unknown coefficient a intervene. There is this constraint on z that say that they have to be a solution of the ODE associated with v, and so there's this extra notation with with the evolving data set associated where z appear. This is an optimal control problem. This is well studied, and so there are well-known characterization of the optimality conditions for this problem, which are given by the Pontryagin maximum principle. And so just to give them quickly, to obtain this the optimality equations, you introduce a costate that is defined, that's called P, and lives in the same space as the variable. So it's an optimal control. I should say what is the control, what is. So in this formulation, you have here the A's are the control variables. And these A's characterize an evolution equation for the Z's, which are the state variables. And the costate, in theory, belong to the space, the dual space to the space that contains the state. Here we are in finite dimension, so we can use we can neglect the fact that it's a dual space. So the costate is a vector that has the same dimension as the Z's, which is n elements of Rd, and there is in this case this Hamiltonian, which is defined by this expression. And so it's just a definition of this function that is a function of P and Z, and has the control as a parameter. And the solution of the equation are characterized, by the fact that there exists a co-state such that these three conditions are satisfied with this boundary condition for the co-state at times t equals 1. There's another boundary condition I didn't put, but that the state itself has to start with the original training data. So there's a boundary condition for z of 0. And so these consistency conditions are necessary conditions for the for local minimum of the control problem. These conditions are also essentially providing the gradient of the objective function. Well, speaking of the differential or the gradient, okay. The gradient is given by this expression, so what I'm calling U here, where you have to compute Z, P, and A is the current variable, so it's a gradient with respect to A. So you compute Z by going forward with this equation. You set P of 1 equals to this expression, and you compute P by going backward with this equation, which is backpropagation. And this is a very simple way to compute the gradient for this optimal control problem. And just, I won't be reading that, but it's just to say that when you discretize, you get something which is as simple and even that looks that is implementing the backpropagation algorithm. Okay, so I have almost everything. Now I still haven't specified how to decide what the space V is, or the reproducing kernel, and there is a one-to-one correspondence between the spaces V and kernel, so we can just decide to choose a kernel. In shape analysis, most of the time, we choose kernels which take this form. It should be matrix valued, but if you're lazy enough, the simple example of matrix valued kernel is a scalar multiplied by the n-entity. And so if you start with a scalar kernel among those that are well known, like a Gaussian kernel or a Mattern kernel, you have immediately a matrix valued kernel by multiplying it by the n-entity. These kernels are actually a bit natural because they provide translation and rotation invariant spaces V, meaning that if you modify V properly by translation and by rotation and translation, the norm of a transform V is the same as the norm of the original V, where the norm of the transform vector field is the same as the norm of the original vector field. So there is this invariance, and it can be natural. It's definitely natural in shape analysis. In this large dimensional problem, it may not be as natural. I mean, you get an invariance by for example, any permutation of the indices. Why would that true? I mean, if you're working in a space of 1D signals, and you're allowed to just permute the time point arbitrarily, why would the norm be the same? And it's a little too much. And you can think of. I didn't implement that in the experiments I'm going to show you, which are very preliminary. But you can think of different forms of kernels in that case, which would be a little more elaborate. And the simplest one is to have K to be a diagonal of, say, forget about the PI, but simply 1D kernel. So K kappa of xi minus yi as a radial basis, but applied only to one coordinate at a time, which is definitely not rotation invariant, but relatively interesting. I'm calling that the naive kernel because it reminds me of naive pies. One more ingredient that is helpful. So I did implement this naive kernel, and sometimes it does actually better than the other kernel. One more ingredient that you can do is, in addition to have this vector field or the evolution equation of z be defined by this expression, which was which had the property to go to 0 at infinity, you may also want to move it using an affine transformation, and that just barely complicates the problem. All right, I think I'm ready. Oh, let me give one more remark. So this is diffeomorphisms, and so when people think of diffeomorphisms applied to, for example, object recognition, there is a deformable template method, which is just you have your template, you have somewhere an image that and you deform your template to see where it fits in the image, and so this is definitely not deformable template, what we're describing here. And the reason, if you look at it, is that the diffeomorphism works on the wrong side of the template. So if you look at the deformable template, for example, for images, a diffeomorphism acts on an image, deforms an image by essentially composing it on the right by its inverse. And so you get the image of a I don't know, letter, and you deform it, you get a letter that looks more or less the same, but it's still identifiable as a letter, it's just deformed. If you apply a diffeomorphism in the space of images, so let's discretize it. I mean, I don't want to have infinite dimensional diffeomorphisms, but let's discretize the space of images. Then you apply the transformation on the left to, say, the very large dimensional vector that consists of all the pixels of the image. So you can apply any transformation, diffeomorphic transformation, to the set of pixels of the image. And as I said, for example, shuffling the pixel is part of the transformation that we consider. And so it's much wilder than deformable templates. And it is actually a very, very large space. But it's may not be large enough. There are some classification problems that cannot be solved after, I mean, by linear separation after applying a diffeomorphism. For example, if you have a situation in which I will show an example immediately, but if you have a situation in which your training data is like that, in 2D, whatever diffeomorphism you will apply to it will not. So this is. So this is, say, class 0, and that's class 1. If you apply a 2D transformation to this data, you will not be able to separate. I mean, there will always be this little circle, or that won't be a circle after transformation, but there will always be this little circle in it. This is not, I'm not treating that as an image, it's the data. So I have points, maybe 100 points or 1,000 points there that represent my data. So think of it as a density, the distribution of the data point. And so even if I flip the coordinate, if I do anything, I will still have a circle within a ring within another ring. So, but what you can do is cheat and add one more dimension. We're ready to work in large dimensions already, so you can add one more. And if you add one more dimension, then the problem becomes trivial. And instead of reading that, I will just show you, well, let me show you the example that I just talked about. So this is the training data. No, this is the test data. The training data had fewer points, but so the test data is like this kind of target, in which so it was a two-dimensional problem, and the only thing is that in that so the XY plane is the original problem, and you add one dimension. And of course, if you add one dimension, you can see immediately from this that it becomes easy. So this is after some rotation, but it becomes. Come on. That should have been a video. Give me 1 second to quit and reload. Now we can see something. So this just shows the evolution, the diffeomorphism evolving. And so it's moving the points, the red points in one direction. Now it's 3D, it has room enough to do that. Moving the red points in one direction, the blue points in the other direction, and they're easy to separate now. So that is what I meant by adding a dimension. So here's a summary of, so the final classifier is ridge logistic regression. A few entries so the choices for the parameters were quite simple. So the number of time intervals for the discretization of the flows was just 10. Data was normalized so that they had a median distance of 1. And the only maybe a little refined thing that is done here is that there is a coefficient here, lambda, in front. Oh, that's not the right lambda. This whole thing used to be multiplied by another lambda, and that's the cost function, the endpoint cost function. So the coefficient in front of that function, so the importance of doing a correct classification is we start with a rather low value, and it's progressively increased, and until the training error reaches a threshold. All the experiment that I'm going to show, the training error at the end is 0 in the data. So I already showed that one. Here another one, which is almost as simple as the previous one, but it's in 3D. So here we're looking at the original data in 3D, and it's just a kind of two rings, so one within each other. So this kind of thing. So it's again, it's not too hard to separate it if you have one extra dimension, and here is the representation of the separation. Of course, this is now it's happening in 4D, and I can only show you 3 dimensions. So the first dimension is always the dimension that corresponds to the linear separation, so the direction along which the linear, which is perpendicular to the linear hyperplane that separates the data. And then I take the rest and I do a PCA for the remaining direction, so that we see the most of the data. So, but this was here. We started with 3D problem and we finished in 4D, and that was quite easy to separate. It's not like it's an achievement. So the first problem, of course, in this problem, linear transformations. Right? This is logistic regression. This is linear SVMs. This is RBF SVM, random forests, k-nearest neighbors, and multilayer perceptrons with 1, 2, or 5 hidden layers. And that's as deep as I want. With the size of data that I'm using, it's not useful to use more layers. But these are easy problem to start with. If you look at these classifiers applied before estimating a diffeomorphism, so to the original data, except the linear classifier that have no chance to work on examples like that, they all perform reasonably well. I don't know why the MLP with one hidden layer was not performing well here. After estimating a diffeomorphism, and you saw what the diffeomorphism does, it really separates the data. It becomes easy to separate in every case. Same thing with the tori that I showed just before. It's not good with linear separation, but everything else were fine, and after the data, it still works fine. A few more comparison here. So now you take the same 3D example with the tori, and you embed it in a 10 or 20 dimensional space. I think, 10 or 20. And you actually combine this with a random rotation just to screw up the random forest. And the results are given here. So if you have 200 training samples, you get these results on the original data, results on transform data, and you can see that in that case, for example, especially look here, the one hidden layer perceptrons does the best, and so the application of the diffeomorphism doesn't find probably the best transformation that allows the data. I mean, we know what the best transformation is because we build the data, but that allows for the separation. But it does still reasonably better than everything else except this nonlinear perceptron. And just to show you, so it's not a video, just to show you what the data was to start with. On the first three principal directions, you don't see much because, well, there's noise, and so it's in 10 or 20 dimensions. And after transformation, as I said, so the training data is always well separated, and sometimes it also works well for the test data. And again, it's projected on a three-dimensional space, which is most representative of the data. Another standard example is a XOR embedded in a 50-dimensional space, and in that case, the transformation could be found that solves this XOR problem. So it is defined here. It's almost the coordinate are 0 and 2, 1 or minus 1, and if you have 1, 1, 0, etc., or minus 1, 0, etc., you're in class 1, and otherwise you're in class 2. And of course, the location of the 1 and minus 1 is random. So if you look at the original data and you're projecting in 3D because you just are looking at very special points, many of them are on top of each other. And after the diffeomorphic transformation and visualize on the main three coordinates, you end up with these results. And just that you can see that on that example, the estimating a diffeomorphism really helped. One more example in which you have radial basis functions, and okay, it's just how the classes are. I mean, it's a complicated definition of the classes, and the results are. It's quite interesting because in that case, SVMs, well, it's radial basis functions, so SVMs do well, and but after transformation, the all classifiers do similarly, and that how the data looked like originally, how it looks like after transformation. So this is the training data, still well separated, and not so well separated, but not bad anyway for the test data. Okay. So this is very preliminary, and there is a big issue here, which is the computational time. Computing, in the implementation I have, I can go, say, to 100 dimensions in 1,000 examples, and not more than that. If I want to work in 10,000 dimensions and many examples, I would have to be creative. And there are some direction in which you can go. The standard SGD doesn't work with this formulation, but there's some ways that can be done. I just want to say also that this was classification. You can also do regression. Here is one example with the target and the resulting regression. So you had the data in the original data set that looks like that. So it's nonlinear function of the data, and the value of the function is represented by the colors. And if you apply regression, linear regression to this data, you get an estimation of the colors, which is not at all matching the truth. And if you do a transformation so that the linear regression works, you get so that the true after transformation, and this is a true after prediction, and you see that the prediction is reasonably matching the data, so that potentially works on regression also. Right, thank you.
Thank you very much, Laurent. Questions? Yes?
So you make a comparison with neural networks at the beginning. So you get a continuous map to another space where you can get linear separation. So I didn't quite understand what you gain by asking for a diffeomorphism. So in the neural network case, you typically go to lower dimension, and it may not be smooth if you're using revenues. So why do you need invertibility?
So you don't, I mean, you can lower dimensions with neural networks, you don't always lower dimensions. So the advantage of diffeomorphism is, the first thing is that you know what you're doing. The other thing is that it's reversible, and so potentially, you can think of programs in which you put your data in a configuration which is looks like a Gaussian, for example, and so that by reversing the diffeomorphism, you have a generative model. It's also, I mean, again, because it's well understood how to regularize, and this regularization approach is really a regularization which is adapted to diffeomorphisms. And of course, it's because I'm working on diffeomorphisms. The two.
Other questions? Yes.
But if the end goal is to do classification and regression, I mean, why not just do the usual support vector machine? I mean, at the end of the day, you want an embedding.
So you do a little more. So there is this embedding, but the support vector machine is only adjusting in one direction in this embedding, if you think of it. And so what this method seems to be doing is also adjusting, at least adjusting in the data space, so that this other embedding becomes easier. And so it's moving in all directions. And it seems to be healthy, at least, for example, the very simple normalization, so having interdistances to be equal to 1, and the median interdistances to be equal to 1, seems to be working well enough for in its examples. The decision of what the kernel size was not a nightmare. It was relatively straightforward. And of course, I tried maybe a dozen examples, different cases, which are not trivial, but that are not everything that could be done. And it seems to improve on SVM. It's rare that, except in this radial basis function, that last example that I showed, it's rare that SVM outperform this method. On the other hand, the multi-layer perceptron, the neural networks work closer to the performances.
Can just a follow-up. So, but then the kernel that you use here to penalize your diffeomorphism, those ones don't depend on the XI data points, right? Like, I mean, here
they do. Oh, well, in the sense, I mean,
you're picking radio basis kind of thing, right? I mean,
yes. What? Yeah.
So this is not the case where you kind of try to regularize the diffeomorphism by putting kind of a generic kernel that would apply for any data set, and then you have an extra term where you try to force.
The only normalization is on the data set. So all the size of the kernel is adapted to the median inter-point distance in the data set. That's the normalization. But other than that, it's generic. It's a Gaussian, it's a latent kernel there. So it's as generic as an RBF, an SVM could be.
Okay, let's thank Laurent.
Thank you.